Okay, it looks like it's time to begin. So let's get started with our presentation. Today we'll be talking about operational automation in OpenStack using LLM and MCP. I'd like to briefly introduce ourselves. My name is Seungkyu, and I work as a principal engineer at KT Cloud. And I have over 10 years in experience as both OpenStack engineer and Kubernetes engineer. And I'm also one of the organizers for the OpenStack Korea user group and ambassador for CNCF Club Korea.
I'm a foundation platform team leader at KT Cloud. I've been working in cloud infrastructure and platform engineering for over 10 years, focusing on OpenStack and Kubernetes and other open source projects. I'm also an active member of the open source community and have shared my work at events like Kubernetes Community Days All and the KT Cloud Summit. It's a pleasure to be here today to talk about how we are bringing AI agents into OpenStack operations.
Okay. Why do we need agent AI when operating managing OpenStack? Most of you sitting here today are the experts in OpenStack. To you, AI must seem unnecessary. However, if you look at this from the user and operator perspectives, we see significant OpenStack challenges. From a user perspective, creating a virtual machine with commands can be quite inconvenient. To launch a VM successfully, you need to look up several details like the right image and the flavor and security group. Furthermore, some of these resources have interdependencies. If you are using a simple dashboard, you are forced to rely purely on experience to determine the correct parameter value. Next, from operator's perspective, issue analysis is simply too difficult. OpenStack is composed of many diverse components, which constantly call upon one another. Because the logs for single actions, like creating a virtual machine, are separated across every single component, correlating them and analyzing the root code is exceptionally difficult. Okay, and we don't want to spend our time in simple repetitive tasks, right? And this is why we decided to apply the agent AI to OpenStack to automate repetitive and complex operational tasks. Our goal is to let users easily ask the large language model for help, whether they want to check or create resources or troubleshoot an issue and like that. So they can quickly identify the root cause and find the solution. And to implement this great idea of automations, our first thought was to use our retrieval augmented generation. RAG is a method where you store specialized data into a vector DB for retrieval. This approach allows an LLM, which typically struggles with specific domains, to provide accurate answers about the domain without extensive fine-tuning. To use RAG, you need several components, vector DB, OCR, embedding model, and model serving. The good news is that KT Cloud is already provided this RAG service, so we can use that without installing the services. This is made RAG our starting point. However, we quickly realized that RAG alone is insufficient for our goals. First, it lacks real-time state awareness. RAG is excellent at retrieving and displaying documents and historical logs, but it cannot guarantee the secure execution or retrieval of real-time resource states, such as variable networks or available zone or security group or something like that. And second, it has limitation in root cause analysis. RAG is useful for suggesting similar past cases, but it is weak at correlating and causal inference. This weakness means it can potentially amplify false alarm or incorrect diagnosis. And our second approach is the incredibly popular agentic AI. We investigated agent AI and found features that made it ideal fit for our OpenStack challenges. That's why we decided to fully implement it. The primary feature of agentic AI is the closed loop from summary to execution. The AI system handles the entire process automatically, and this approach moves beyond simple description to what RAG provides to operational action. Crucially, this structure is highly flavorable for reducing NTTR. And so, what is the closed loop? How exactly does the closed loop work? First, the user's natural language input is received, and if that and performs real-time calling and executing using the MCP tool. And finally, the agent validates the result, summarize them, and connect with any necessary follow-up actions. And in simple terms, this system independently understands and verifies executes and reports on a command, completing the full automation cycle. The second key feature of agent AI is its ability to integrate with the real-time state and external systems. We can instantly query the current state, butter, and the network values, and for OpenStack components like Nova, Cinder, and Keystone. And furthermore, of course, the two external API, such as the PagerDuty or observability or the CMDB, are made using a single unified MCP inference. This whole approach makes what is called the decision on truth possible. It means we act based on verified real-time facts, so our decision and actions are always reliable and fact-based. Let me now outline the core components that make up our agent AI system. First, we have the large language model, which can think of as the brain of the system. And next is the system prompt. It's very important, and which define the behavior rules or what actions the LLM should take. Finally, we have the MCP server. This is the tool that connects and interacts with the external resources. So, what is the sequence of components for our agent AI? First, the process begins with the input. When user request comes in, the agent runtime makes its initial call to the LLM. This call bundles three essential pieces of the context: the custom prompt and tool definition and schema, the user messages. The system prompt, which defines the system's behavior rules, and the tool definition and schema retrieved from the MCP server, and the user message. The second step is the decision phase. The LLM either gives the answer right away, or if it decides a tool needs to be called, it shows which MCP tool to use and what argument to include. The third step is tool execution. Based on the LLM's instructions, the MCP client receives that directive and sends a request to the appropriate MCP server. The server then execute the action and returns the execution result, which is in form of structured data. The fourth step is the loop phase, which only runs when needed. In this phase, the system proof stays active, and the LLM takes the result of the last execution as new context to generate the next true call or the final answer. The final step is the output. The LLM's final response is delivered to the user. It's important to note that any necessary guardrails such as the pulse check, approval workflows, or RBAC are automatically checked before the tool execution step. In short, the system provides the AI with its rule of behavior, and the actual MCP core follows a strict sequence. To summarize the entire agentic AI workflow simply, when a user request arrives, the agent runtime passes the system proof and the MCP tool definitions to the LLM. The LLM decides on the appropriate to call, and MCP client executes the MCP server, and the result can fed back to the LLM to generate the final response. How do we actually build the agentic AI? There are several great open source tools available for creating agentic AI. You have Google Agentic Development Kit, you have LangChain and LangGraph, and there are tools like AWS Strength. However, all of these tools are one significant drawback. They all require you to program the agent AI with code. Now let's talk about Kagent. We chose Kagent as our primary tool for building agentic AI for several key reasons. No code development requires. Crucially, the Kagent allows to build agent AI without the code. And the built-in UI, it provides a built-in chatbot UI for interacting with the AI. Next is the CNCF Sandbox project. Most importantly, Kagent is a CNCF Sandbox project. This is providing strong community backing and significant potential for future development and the adoption. So, let me briefly introduce the Kagent, because I love the Kagent. We have used Kagent, so I show how to build the Kagent in my system. Kagent is a very popular project since it was first announced on March 17th, 2025. It has gained more than 365 stars on GitHub in just 2 weeks. And it is a currently a CNCF project, a CNCF Sandbox project, and it's structured around the agent catalog composed of 3 core elements: the agent, and the tools, and the framework. Let's quickly define this. The tool is an entity style capability that allows the agent to interact with cloud native system. Examples include viewing pod logs and querying Prometheus metrics or generating new resources. Agent is an automated system. It uses one or more tools to plan and execute the tasks, analyze the result, and define its action. The framework provides simple declarative APIs and controls to easily build and run your agent. Kagent is designed for easy installation and execution directly on top of Kubernetes. Powerful use case demonstrates our closed-loop automation action. When our workflow is failed, Kagent can immediately trigger on automatic rollback, and following the rollback, the the system would automatically create an issue and perform root cause analysis and finally source the concrete solution. I'd like to explain how K-agent operates under the hood. K-agent relies on several custom resource definitions, but three are especially critical: the agent and MCP servers and remote MCP servers. First, let's look at setting up the MCP server. We deploy the OpenStack MCP server as a standard Kubernetes deployment, and then you register it using a custom resource for remote MCP server. This OpenStack MCP server can be something you develop in-house or existing source implementation. Next, to deploy the OpenStack agent, you write a system prompt and register it as an agent CR. And during the K-agent controllers reconciliation cycle, the agent CR is translated into a format recognizable by the Google Agent Development Kit. And this translated agent CR is then deployed in the Google ADK, which results in the new OpenStack agent AI running as a Kubernetes deployment. This concludes the explanation of the agent AI concept. And next, Seungkyu will take over the details, the specific implementation and method, and provide a live demo.
Next, I'll explain how we apply the K-agent system in our real system that Seungkyu described earlier. We have two main goals for implementing K-agent. The first is to manage the OpenStack resource life cycle using natural language rather than a predefined CLI or UI console. In this process, requests should be translated more accurately and efficiently through a specialized OpenStack agent. The second goal is to analyze and resolve errors with simple natural language requests in specific failure situations. To achieve this, the main agent, which is A2A agent, enables seamless communication between the OpenStack agent and the observability agent. Before explaining the K-agent integration system, let me first introduce our Next platform architecture. KT Cloud's Next platform is our cloud-native foundation. It runs OpenStack on Kubernetes with OVM-based unified networking. On top of this, we've built K-agent, our AI automation layer that connects LLMs with real infrastructure through MCP servers. The next observability system is built with a cloud-native LGTM stack combined with OpenTelemetry. Data sources are categorized into application, platform, and infrastructure, and each layer's data is collected through the LOE cluster, stored in Mimir, Log, and Tempo, and visualized in a unified data source via Grafana. Since the OpenStack system runs on Kubernetes, we can monitor metrics through Mimir, logs through Loki, and visualize everything seamlessly in Grafana. Now let me explain how K-agent works internally through its system architecture. K-agent provides a UI interface which allows users to easily create or select agent. And just like other element-based interfaces, user can send a prompt message to request specific operations or tasks. Within the system, K-agent manages two key custom resources, agent and remote MCP server. By default, K-agent includes several built-in agents and their corresponding MCP servers. Users can also define their own agent and remote MCP server CRs to extend K-agent with additional agents or external MCP servers. For example, the observability agent and the K-agent Grafana MCP are built-in components provided by K-agent, while the OpenStack agent and OpenStack MCP server are custom modules that we developed. Through the K-agent UI, you can select an agent and enter prompt. You can also choose to use a single agent or a super agent like main agent, which orchestrates multiple agents together for more complex workflows. Each agent communicates with each connected MCP server. The Grafana MCP server interacts with the Grafana API to retrieve observability data, while the OpenStack MCP server calls the OpenStack API to manage cloud resources such as instance, networks, and volumes. Let me explain agent in detail. The agent area consists of three agents. The observability agent is an AI agent specialized in monitoring, leveraging Prometheus, Grafana, and Kubernetes. Grafana stores endpoint for data sources such as Mimir, Loki, and Tempo, and the observability agent retrieves specific monitoring data through targeted queries. The OpenStack agent is an AI agent optimized for managing OpenStack resources. We created custom agent with only system prompt in K-agent. K-agent automatically builds and runs the corresponding agent. The main agent acts as a super agent, orchestrating both the OpenStack agent and the observability agent using the A2A protocol. Through K-agent, it is also possible to create agents that can communicate with each other by the A2A protocol. Let me explain how we implemented the MCP servers in our system. The MCP protocol is designed to enable real-time tool execution and agent-to-agent interaction. Within K-agent, we've implemented two types of MCP servers, OpenStack MCP and Observability MCP. Our OpenStack MCP server was initially developed using Fast MCP, which runs over HTTP and handles requests in a transaction way. However, this design was faced a limitation. Since HTTP is stateless, it could not maintain a persistent connection with K-agent, which required continuous streaming interaction. To resolve this, we developed it using streamable MCP, allowing proper bidirectional communication and real-time coordination with K-agent. This new design ensures that OpenStack resources operations such as instance lifecycle management, network creation, and error analysis can be executed instantly through the agent interface. On the other hand, we didn't need to develop a separate MCP server for observability. K-agent already includes a built-in Grafana MCP, which directly integrates with Mimir, Loki, and Tempo as data sources. Through this built-in graph and MCP, the observability agent can run monitoring queries in real time, collecting metrics, logs, and traces, and feed them back into the reasoning group for AI-driven analysis. Let's talk about the system prompt, which plays a critical role in defining how each agent behaves. The system prompt essentially defines the agent's behavior. It acts like a rule book that tells the agent what to do, how to respond, and how to make decisions in different situations. It also ensures safety by embedding the necessary policies and guardrails that prevent the agent from making unintended or risky actions. In other words, it keeps the automation process stable and trustworthy. Finally, a well-designed system prompt improves overall outcomes. When the prompt is written clearly, the agent can interpret user intent more accurately, leading to better, more reliable automation results. Let's look at how we improved our agent's behavior using the system prompt. Users often mixed what they want to do with what information they needed. As a result, the agent made unnecessary round trips, asking too many follow-up questions, and users couldn't clearly see how far the process had progressed or what partial results were already available. To solve this, we introduced an intent-first analysis approach. The agent first determines what the user is trying to accomplish and then classify the request as either an action or an analysis. For action type requests, we use an autopilot mode. The agent performs slot filling, presents a clear execution plan, requests one-time confirmation, and then proceeds seamlessly. For analysis type requests, we use parameter filling, applying safe default to minimize missing information. In addition, when multiple resources are needed, the agent performs batch lookups, batching everything into single request instead of multiple calls. This approach produces significant improvement on unified flows with fewer sections and less token usage. Clear visibility into plans and progress. Now, let me walk you through a short demo showing how we create an instance using the OpenStack agent in K-Agent. On the right side of the screen, you can see the K-Agent UI. Here, the user simply types a natural language prompt, such as create a new server instance, use the zeros image, and so on. I applied that this demo shows some Korean language mixed because we define the system prompt in Korean. When the command is executed, the agent first analyzes the request and generalizes an execution plan. After the user gives one more confirmation, the agent automatically sends an instance creation request based on the predefined specifications in the system prompt. On the right side, we are monitoring OpenStack logs through logging, and the left side shows the OpenStack CLI that can execute command in real time. After sending the creation request, we check the instance status. And unfortunately, we can see that the instance appears in an error status. At the same time, the right panel shows the error logs detected from the OpenStack services. So in this demo, the instance creation failed, but it clearly demonstrates how K-agent interpret natural language, build an execution plan, and integrate with OpenStack to perform real operations. Now, let's look at how the main agent in K-agent performs automated error analysis. In this demo, the user simply enters the UUID of the instance into a prompt and asks the agent to analyze the error. Without any additional input, the main agent automatically gathers instance details, checks the related logs, and searches for error patterns associated with the specific UUI. In this case, the agent finds that the instance creation failed due to an issue in default. Specifically, an incorrect RBD secret configuration registered in the system. Once the issue is identified, K-agent also provides a recommended solution describing the exact steps needed to correct the secret information and restore normal operation. So through this process, the user doesn't need to manually inspect logs. With just simple information, the main agent performs full context analysis. After identifying the root cause, we discovered that RBD secret configuration in the single Haan chart was different from the one registered in default. To fix this, we updated the single Haan chart configuration and we deployed the chart. As you can see on the screen, the single parts are restarting as part of the redeployment process. In this demo, the playback speed and editing make it like the part restart very quickly, but in reality, the restart process doesn't happen that quickly. Once all parts were successfully restarted and become healthy, we attempt to instance creation request again. This time, the agent analyzes the prompt, retrieves a matching or similar instance specification, and then presents a confirmation message before execution. After we confirm the plan, the instance was created successfully. And also validate the status of instance. So this demo demonstrates how K-agent can not only identify the cause of failure, but also guide you through a fix and verify that the instance creation works correctly after the issue is resolved. To summarize, our goal is to build a closed-loop AI agent with servers as the key to achieving true operational automation. Through this approach, we can reduce MTTR, streamline troubleshooting, and deliver a much better experience for both operators and users. Looking ahead, our next step includes adding a RAG agent to enable documentation-based reasoning and continuously refining our system process to make the agent even more intelligent, reliable, and context-aware. Thanks for attending our presentation. And if you any, the time's over, so if you any questions, please come to us later. Thank you.
Go.